Okay, so the format of this talk might be a little different than the other ones in the sense that I'm not actually here to tell you about any research results. I'll say some at the end. I'm here, this is more like a class lecture. There's a really nice technique called chaining, and it has applications to lots of TCS, including sublinear algorithms, which I'll mention at the end. But I'm here to just tell you about what chaining is, okay? So I want you to understand chaining when you come out of this. Just a show of hands, who knows Gordon's theorem or has heard of it? One, okay, so you'll learn something new, good. Or who's seen generic chaining? Who's seen generic chaining in some form? Okay, so, okay, few people, so good, so that's good. So what's this talk about? You know, what's chaining? So this is a situation that we see a lot in TCS. We have a collection of random variables, and we want to say that with high probability, they're all small, okay? And I remember when I was taking Karger's randomized algorithms class as an undergrad 10.5 years ago, my friends and I used to call it the Chernian bound because we would just do it all the time. We didn't like to say Chernoff plus union, it wasted syllables. And today's topic is beating the union bound. Okay, so chaining is a systematic way of dealing with this situation and doing better than the union bound. And disclaimer, this is an educational talk about ideas which aren't mine. Okay, this is not well, I'll mention some research that's come out of that's used chaining results, but that's not the focus of this. The focus of this is to get you to be chaining masters. Okay, so first off, I'm going to start with a toy example. Well, not toy, actually. No, forget about toy. It's a real example that probabilists care about a lot. Okay, and I'm going to get you to know some of the things that those folks know, and then I'm going to show you that the same techniques that they use actually apply to our problems. Okay. Okay, so first example. Here we have a set of vectors in Rn. They all have unit L2 norm. This is the unit ball of L2n. Okay, a bunch of unit vectors, and our random variables look like this. They're a collection of vectors z sub x, where x is in this set T, and z sub x is g dot x, where g is a Gaussian vector with ID entries, and x is this thing in T. And I want to understand something called the Gaussian mean width of the set T, which is the expectation of the max of those random variables. Okay. So questions about? I mean, you should hopefully. This definition should work for you because for the next many slides, I'm just going to be talking about g of t. Okay, so remember we're trying to say that we're trying to bound the max of a collection of random variables. This is not the soup of the expectation. This is the expectation of the soup. Okay, so I'm saying that say by Markov, with constant probability, the max will be bounded by whatever this expectation is. You can get high probability bounds. I'll say something about that later. Okay. So everybody's happy, hopefully. And how can we bound g of t? So I'm going to show you 4 ways of doing it that are progressively more sophisticated. Okay, and then we'll move on to some applications. Good. Okay. So that's what this talk is. Okay, so the first thing is the thing you're used to, which is tail and union bounds. Okay, the Chernian bound. So focus on a particular x and look at g dot x, right? G dot x is a sum of Gaussians, sum of GIXI. So a sum of Gaussians is a Gaussian, and the variance is add. So what's the variance of g dot x? It's 1, because x has unit norm. So there's a bunch of Gaussians, all of unit norm. So I can do my Chernian union bound thingy, okay? And I can say, look, the expectation of a random variable, that should really be probably the soup is bigger than u, right? The expectation of a random variable is the integral of a tail bound. There's a soup inside that probability that I forgot to write. Oh, there's the soup now. And I'll just split up the integral into 2 pieces. I'll integrate up to some u star that I'm going to choose in a second. And then I'm going to integrate from u star to infinity. And that thing, I'll just use Gaussian tail bounds, right, and a union bound. So there's my union bound. And this thing, probabilities are never bigger than 1. So I get that this integral is at most u star. That thing is at most this thing, okay? And if I set u star to optimize this bound, I basically get root log t. Okay? So that's what you expect. If you have t Gaussians, the biggest of them is going to be root log t. Okay. So that's one way of doing things. And in general, I mean, there are examples of t's where this is the right answer. Okay? But this is not, as you're going to see soon, this is not the answer for all t's. I mean, this is not always tight for any t. Okay. So that's step one, which you're very familiar with. Or method one, which you're very familiar with. So method two is also something that you're probably familiar with, or, which is to use an epsilon net. Okay, so S sub epsilon is a collection of vectors such that everything in T is within epsilon in L2 distance of something in S sub epsilon. Okay. So for any g dot x, I can write I can write x as x prime plus x minus x prime. And then g dot x is g dot x prime plus g dot x minus x prime, where x prime is the closest person to x in the net. Okay? So now if I care about the expectation of the soup, well, the expectation of the soup of this part is just the Gaussian mean width of S sub epsilon. Okay? And this thing over here, you know, if I take the dot product of two vectors, it's at most in magnitude the product of their norms. So this has norm g, the L2 norm of g. This has norm at most epsilon because I took an epsilon net. And the bottom line is expectation of the L2 norm of a Gaussian is like the square root of the dimension. Okay? So I wrote down a very short proof. You know, that's why. This thing we know from the last slide by union bound is at most square root log the size of the net plus epsilon times this thingy, which is root n. Okay? So just some notation. This number here for me, usually called a covering number, it's the smallest size of an epsilon net, right? So the size of S sub epsilon, I can choose S epsilon to be the smallest epsilon net there is, okay? So we've shown another bound. Okay, and you can choose epsilon to optimize this bound, right? So the last slide is a special case of this slide where epsilon was 0. Okay. So everybody's with me? Good. Okay, so now I want to show you method 3. Okay, and method 3 is also something, by the way, all the methods I'm going to show you are, I mean, nothing's too crazy, okay? It all makes sense, I hope. Okay, good. So method 3 is to take a sequence of epsilon nets, okay, where S sub k is a 1 over 2 to the k net of t, where k goes from 0, 1, 2, 3, you know, k is like positive integers or non-negative integers. Some notation, pi sub k of x is the closest points in sk to x in t, okay? And delta kx is, so think of delta kx is take the person who's close to me in the k net and take the difference with the person who's close to me in the k minus 1 net, right? And just by triangle inequality, this will have small norm, right? Because I can take triangle inequality where I can take pi k of x to x, and then I can take x to pi k minus 1. And those are both small when k is big. So delta is going to 0. And pi k is going to x, is like becoming like x. And I'm going to just assume the stuff I'm saying now you can apply even when t is an infinite set. But I'm going to assume that t is finite. And that's without loss of generality, because step 1, what I can do is I can just do the last slide where epsilon is super, super tiny. And then I can apply this method to the net from the last slide. And the net is finite. Okay? And I can write x as pi 0 x, as pi 0 plus, pi 1 minus pi 0 plus, pi 2 minus pi 1, etc. So I can write x as an infinite sum of vectors. So g dot x is this thing plus an infinite sum. Okay? So now I can do the Gaussian mean width, which is the expectation of the soup, is at most an expectation here plus a sum of all these expectations, linear expectation. And this is 0 because, remember, pi 0 of x is just someone who's close to me in a 1 net. 1 over 2 to the 0 net is a 1 net. And these are all unit vectors. So my 1 net just has size 1. So my 1 net, there is no soup. There's only one single pi 0 of x. And this is just a Gaussian. The expectation of a Gaussian is 0. So this term disappears, and I'm left with that. And now, what I'm going to do is, I'm basically going to apply slide 1, the union bound, to every single one of these for every k. Right? And the union bound gives me square root log the number of vectors. Right? How many vectors are there? How many possible delta k's are there? Well, it's the covering number with a 1 over 2 to the k net times the covering number with a 1 over 2 to the k minus 1 net, which is at most the square of the finer net. But logs don't care about squares. Log of a square is just a constant factor anyway. So I get something like this. I get the Gaussian mean width is at most the sum from k equals 1 to infinity of square root log of the size of a 1 over 2 to the k net. But now notice these are not unit vectors. These are vectors of norm at most 1 over 2 to the k by triangle inequality. So I pick up I get a 1 over 2 to the k there. The standard deviation of that Gaussian is 1 over 2 to the k. So I get 1 over 2 to the standard deviation times square root log the number of Gaussians. So, okay. And something that people often do is they bound this sum with an integral. This is the standard thing. And people call that Dudley's theorem. But it's something very simple that you're used to seeing these arguments. Is everybody still with me? Okay. Good? Okay. So now let me move into generic chaining. Okay. And before I actually give you the proof, it's also going to be a short proof. All of these are short proofs. Again, without loss of generality, the size of T is finite. And I'm going to have a sequence of like net looking. They're not epsilon nets. They an epsilon net is a set with the property that everyone is within epsilon of someone in the net. These don't have that property. They're just they're just finer and finer approximations of T, but they're not nets. Okay, you'll see what I want out of them soon. Where T0 has size 1, just like before the last slide with S0. And Tk I restrict to have size at most 2 to the 2 to the k. And I'll show you in a second why you would define it this way. Okay, an exercise. I say exercise, but actually I'm going to explain it to you. So exercise. Dudley's theorem on the last slide, I claim is equivalent to, let me just rewrite this. Can people see this? Is it too dark? Okay, so last slide we had a sum over k from 1 to infinity of 1 over 2 to the k times square root log of the covering number. That was the last slide. Okay, that was Dudley before you turned it into an integral. And I claim that that bound and this bound are the same thing. Okay? Up to a constant factor. And why are they the same thing? Does anyone have an idea of why they're the same thing? I guess I'll just give you 5 seconds. Okay, so I'll just tell you why they're the same thing. So remember, first of all, what is this? This number is just square root log the size of Tk, right? Which looks a lot like square root log the size of the covering number. This should really be S epsilon. T, no, that's T. Yeah, good. So that looks like, that's square root log the size of Tk. That looks a lot like that. And what's really happening here is, at first I give you very few points in your, in your net. Okay. First of all, in this formulation, if I'm trying to minimize this expression, then Tk should be the best net I can make with 2 to the 2 to the k points, right? Because I have the soup on the inside of the sum here. Okay. So this is kind of the inverse. Like I give you a size for the net, and you have to make the best net you can with that size. And the point is, for a while, the best net you can make is a 1 net. When I say for a while, I mean for the first few k. But notice that this is geometrically increasing with k. So here you're basically getting like something very close to 1 for a while, for many k's. And this is just geometrically increasing, so it's dominated by the last term. Okay? And then this starts being close to like 1/2 for a while. And then for the next few k, this is increasing geometrically, and then it's dominated by the last k while this is close to 1/2. Okay? So because you put this exponential term here with k, it's always, for every rough approximation of the net quality, you're getting a geometrically increasing sequence that's dominated by the last term, which in the end, the last term is going to be square root log of like the net size. So this summation here is up to a constant the same as this summation here. So this is just a rewriting of Dudley's theorem. Okay? And what doesn't follow from anything I've said is that actually what Fernique showed in the 70s is that this soup over x can actually be pulled outside the sum. And it's still true. It's still true that the Gaussian mean width is at most this if you pull the soup outside the sum. Okay? So this now is looking very different from give me the best net you can at every scale. Because if the soup is outside the sum, then for different x's, I might want to approximate them differently at different levels. Does that make sense? Okay. And so this is what Fernique showed. And I put an asterisk because Fernique didn't actually do it. He didn't actually write down his bound in this way. He had some measure theoretic definition of, basically, this is a very discrete thing. I'm finding these sets of size 2 to the 2 to the k, and I'm trying to minimize over the sequence of sets. He was trying to minimize over some measures, okay? But Talleyrand rewrote Fernique's argument in this way and defined it this way. And Talleyrand called this expression here, this inf over sequences satisfying this of this soup, he called it gamma 2 of t. Okay? So I'm going to show you that the g of t is at most gamma 2 of t. Okay, and the proof of Fernique's bound is same like before with the net argument. G of t is at most this pi 0. So now pi 0 is the closest point in t0. And delta k is the difference between the closest point in tk to tk minus 1. These are not nets anymore, though. Okay? And the key thing to note about these random variables is if I call, okay, if I look at a particular one of these random variables, it's a Gaussian whose standard deviation is this value right here, is the norm of that vector, right? And what's the probability that a Gaussian exceeds its standard deviation by more than a lambda factor? It's like e to the minus lambda squared. So what's the probability that I deviate from my standard deviation by this factor? It's e to the minus that squared. There should be a minus sign. E to the minus t squared 2 to the k over 2. So the probability that there exists an x and there exists a k such that yk is big is by a union bound over all k. It's a sum over all k of how many different delta k x's are there. There's 2 to the 2 to the k squared at most, right? Because it's a difference of two guys in these nets of that tail bound. Okay? So this is the main thing to note. And now what we're going to use is the expectation of a random variable, this one, is the probability that, it's the integration of the tail bound, just like we did in the very first slide. And using this property, what we're tempted to do now is a change of variables. So I'm going to set u to basically be t times gamma 2. And when I do a change of variables, gamma 2 just pops out, right? And then I have this integral, the integral from 0 to infinity, the probability that this is bigger than that dt. Okay? But the last slide, for this random variable to be bigger than this expression, it must be the case that there is some x and k such that this thing is bigger than that, right? If all x and k's, this was smaller than that, then the sum would be smaller. So the fact that the sum is too big means that there is an x and k that deviates by too much. So I can break this up. I can, again, break this integral. This is just a very small technical thing into an integral from 0 to 2, and then an integral from 2 to infinity. of the expression I had on the last slide. And the reason I did that is just because when t is 2, e to the minus 4 over 2 is like 7 point something, which is bigger than 2. So this is super doubly exponentially decaying faster than this thing is increasing. This is like 4 to the 2 to the k. This is like 7 to the minus 2 to the k. So this thing is just a constant. So at the end of the day, I get that everything is gamma 2. Okay? And that's what we just proved. And Talleyrand showed, I won't show it today, it's called the majorizing measures theorem. And the reason measures appears in the name of the theorem at all is because Fernique's original formulation dealt with minimizing over measures. But as I showed it to you now, it can be rewritten by Talleyrand in this discrete way. Talleyrand showed that not only is g of t at most gamma 2, but it's at least gamma 2 up to a constant, no matter what t is. So this is like an instance-wise optimal way of bounding these random variables, the max of these random variables. Okay? Okay, good. And you could ask yourself, are these bounds really different? I showed you 4 different methods. So Dudley gave you something like that. Talleyrand, well, Fernique pulled the soup on the outside. And Dudley is not optimal. So I'll leave it to you as an exercise. If you take t to be like the unit ball in L1 in n dimensions, then first of all, we know what the answer is, right? We know what the answer is without doing any kind of net arguments because the dual norm of L1 is L infinity, right? How do you maximize g dot x where x is in the L1 ball? You put all the mass on the largest coordinate of g, and that gives you g infinity. And the expectation of g infinity is root log n. Okay? So we know by Talleyrand's theorem that since g of t is the same as gamma 2 up to a constant, there must be a sequence of nets or a sequence of these tks that gives you root log n. And as a homework exercise, you can try and find them. Okay? You can do it. If you try and use Dudley, Dudley is all about getting the best nets you can at every scale, right? For every k, this is Dudley. For every k, I'm trying to find the best net I can. And you can convince yourself that actually the nets of the L1 ball, covering it by L2, are not as small as you'd like for Dudley to give you the right bound. Dudley will actually give you log to the 3/2, whereas the true answer is root log. Okay? And if you just try a simple net argument without using a sequence of nets, forget it. I think you get root n. You're exponentially off. Okay, so there's a huge difference between these different methods, even in this simple case. Okay, so so far I just talked about the expectation of the max, but what if you want to know the max is small with high probability? The usual approach is to do the moment method. Actually, you bound the moments of this thing for some large moment, and then do Markov. And you can bound these moments using chaining too, and I put a reference there if you want to read about that. But it's similar kinds of arguments. Okay, and now I claim, back to, this is not a probability workshop, this is a workshop on sublinear algorithms. I claim that these techniques I've shown you have been used in TCS, specifically things that we care about in this workshop, but other things too. So I work a lot on kind of JL and Johnson Lindenstrauss and compressed sensing kinds of things, so that's why I guess I have a biased first 3 bullets that I put here. But if you want matrices that have the restricted isometry property for compressed sensing with fast matrix vector multiplication, one way to do it is to sample rows from the Fourier matrix, and the analysis that tells you that that thing satisfies RIP, basically all these papers use chaining. Okay. If you want fast JL, the first fast JL paper was by Aylon and Chazelle in 2006. And there have been improvements since then, and kind of the best bounds that we know how to get are using chaining. I also had some work on understanding sparse JL for arbitrary point sets that also use chaining. This very recent paper understands the fast JL transform for arbitrary point sets, also using chaining. And then there's Gordon's theorem, which I'm going to tell you on the next slide. I think only 1 or 2 people raised their hand for Gordon's theorem. It's also been used for approximate nearest neighbor, estimating cover time of graphs, list decodability of random codes. Okay, so just think to your childhood, or your life. Okay, so I'm sure you've arrived at many situations where you needed to bound the max of many random variables. And the usual thing is get a tail bound and union bound, okay? And the point is that's not always the right thing to do. I mean, you'll get a bound, but the point is you might not get the real bound, okay? You're just settling for something that's not the truth. Okay, so I only have a few minutes left, so let me give you an example of one of these applications, and I'm going to take it back to Gordon back in '88. Okay, so instance-wise JL bounds. So I showed you expectation of the max of all these Gaussian random variables. But if you really paid attention to the Gaussian proof, what really mattered was between two random variables, there's a distance function between those two random variables. For the Gaussian case, the distance function was the L2 distance of the underlying vectors. And what you really cared about is that the decay of the decay of a difference of those two random variables depends on the distance in that underlying metric space. Okay? So whenever you have that kind of property, that your random variables can be indexed by vectors in some metric space, or elements in some metric space, and the decay properties depend on distances, you can do the arguments that I just showed you. Okay? And there's a theorem by Kramer, Mendelssohn, and Rahut that does such a thing, where here, okay, so let's say these sigmas are just Gaussians, okay? They can be random signs, anything that decays at least as fast as a Gaussian. And let's say you have a collection of matrices, script A. And what I care about is that for all matrices, I want to make sure that none of them deviates by their expectation. The A sigma L2 norm squared minus the expectation, none of them deviates by too much with high probability. And you can get a bound that, surprise, surprise, depends on gamma 2. And the underlying metric is the operator norm of the two matrices. And it also depends on the radius of the family of matrices, or diameter, under Frobenius norm as well as under the operator norm. And I'm not going to show the proof today, but it uses similar ideas to what I showed you, plus extra tricks. I recently there was a summer school in Madalgo recently, and I showed the proof there and put it in lecture notes if you want to read the lecture notes. Or you can read the original paper. Okay. Now, Gordon's theorem. Gordon's theorem says if you have a subset of unit norm vectors and an epsilon, and pi is a JL matrix, random signs, random Gaussians, something like that, then as long as the number of rows in your JL matrix is at least the square of the Gaussian mean width over epsilon squared, you'll preserve all the norms of the vectors. This is the JL condition, right? So you'll preserve all the vectors. And JL T will be like all the normalized difference vectors in your input data. Okay, and I claim that this is just a corollary of, of course, Gordon did it in '88. This is 2014, so Gordon did it a different way. Actually, Gordon did it even before gamma 2 was defined. Okay, so he definitely did it a different way. But now that you all are chaining masters, you'll just get it immediately from this chaining result. Why? Here's my family of matrices. So say X is a vector I want to preserve for JL, and I'm going to define a matrix A sub X that looks like this. I just write X along the rows. There are M rows and Mn columns, and I divide by root M. And notice that, well, you can verify it offline if you want. The squared norm of pi x is exactly the same as the squared norm of AX sigma, where sigma is concatenate all the rows of your JL matrix into a single vector. Okay, good. So now really what we're trying to say is that all the AX sigma squareds are close to what they should be. But that's exactly Kramer, Mendelssohn, and Rahut. For Kramer, Mendelssohn, and Rahut, we need to understand gamma 2 under the operator norm. And we also need to understand the Frobenius radius and the operator norm radius. Well, okay, let's look at the distance between two matrices under the operator norm. Notice that AX minus AY is the same as A sub X minus Y. What's the operator norm of this matrix? What's the operator norm of a matrix A in general? You look at the eigenvalues of A transpose A and you take their square roots. Okay, those are the singular. That's the operator norm of a matrix. Okay, it's the largest of those eigenvalues after you take the square root. So take this matrix and look at A transpose A. Right? A transpose A is a block diagonal matrix that has XX transpose on every single block. what's the eigenvalue of, the non-zero eigenvalue of XX transpose is the squared norm of X, which is 1. So if you take it A transpose A, the non-zero eigenvalues are all 1 divided by m, because there's a 1 over root m that got squared, which means that the operator norm is the square root, which is 1 over square root of m. Okay, so in general, if you have a vector x minus y here, you'll get x minus y transpose, which has eigenvalues x minus y L2 norm squared. So you get this. So distances of these matrices are exactly different distances in the original vectors, which means that if you're looking at gamma 2 of this family of matrices, it's the same as gamma 2 of the original vectors under the L2 norm. And by the majorizing measures theorem, which I didn't show you the lower bound, I showed you the upper bound, that's exactly the same as the mean width. Okay? And the Frobenius norm you can verify offline is 1. The largest operator is 1 over root m. So what this tells us is that this max deviation is at most the square of the Gaussian mean width over m plus g of 2 over root m plus 1 over root m. You set m to make this thing at most epsilon, so m should be this, which is exactly Gordon's theorem. Okay? And, people care about consequences of Gordon's theorem in our community. If t is less than infinity, notice that g squared of t is at most log the size of t, just by a union bound. That's JL. So JL is a special case of Gordon's theorem. Offline, you can verify if t is a d-dimensional subspace, the mean width is d. That people call that subspace embeddings in our community, which people use for large-scale linear algebra, fast regression, low-rank approximation, etc. If you have all k-sparse vectors, you get k log n over k. People call that RIP. So all these theorems in different domains are just corollaries of Gordon's theorem. And there are more applications where basically different t's. Constrained least squares gives you a different t, manifold learning gives you a different t, et cetera, okay? Okay. And chaining isn't just for Gaussians. I think I'm out of time, basically. Is that right? Okay, so you can even, I'm not going to show you this because there's no time. But even in situations where there are no Gaussians or sub-Gaussians in your random variables that you're looking at, you can there are techniques to artificially insert them, okay, into your problem such that at the end of the day you need to bound Gaussian mean width of something. Okay, so I'm not going to show you that, but it's been done. Bam, okay, so the end. And I'd like to put a plug for a workshop that's next summer. It's going to be on concentration of measure and chaining right after Stock, which is also in Boston. So you can stay in Boston for 2 more days. We're going to bring people who actually know this stuff, as opposed to me. Okay? And you can learn more and see applications, et cetera. Okay? So that's all I have to say.